this lecture on the particular course on computer aided power system analysis. In the last lecture, we have discussed about the generation outage sensitivity factor. In this lecture, we will start talking about the line outage sensitivity factor. Now, before we discuss about what is meant by line outage sensitivity factor or rather how to calculate this particular line outage sensitivity factor, we should first look into the concept of Thevenin equivalent circuit as observed from any particular bus in a large power system. So, first let us look at the concept of Thevenin equivalent circuit. So, we have Thevenin. So, we are talking about today Thevenin equivalent circuit. So, Thevenin equivalent circuit. Now, we know from our basic power system analysis whatever we have done, that we know that I vector I is equal to matrix Y into vector V. Vector I is the bus current injection vector vector V is bus voltage vector, and this is bus admittance matrix. Now, if there is n number of buses in my system, so then in that case this is n cross 1, this is n cross n, and this is n cross 1. And we note that, we just recollect that I vector is essentially I 1, I 2, I n transpose T, and V is V 1, V 2, V n transpose T. Here we also have to note that all these currents I 1, I 2, I n, V 1, V 2, V n, they are all essentially complex quantities, but taking or rather doing an abuse of the notation, we are not putting any overbar over any of these quantities, because we have already put an overbar to denote I and V are to be vector anyway. So, now from this we can write down that V is equal to Y inverse into I, or in other words V is equal to Z I, where Z is the we call bus impedance matrix. Now, suppose due to some reason this vector I is being perturbed by a vector delta I. So, that means the injected current at bus 1, that is I 1, is being perturbed from I 1 to delta I 1. Similarly, injected current at bus 2 is being perturbed from I 2 to delta I 2, and so on and so forth, and injected current at bus n is being perturbed from I n to delta I n, right. And so, then therefore, if this is perturbed, so then we can say that this is nothing but I plus delta I vector. Why this particular delta I vector is obvious, that this delta I vector is nothing but delta I 1, delta I 2, delta I n transpose. Now, because this I vector is being perturbed from its original value to I plus delta I. So, then therefore, as a result this V vector will also be perturbed from its original value to V plus delta V. So, then therefore, we can write down that V plus delta V is equal to Z into I plus delta I. Please note that this V is changed from V to V plus delta V because of this change of I from I to I plus delta I. So, from this we know that V plus delta V is equal to Z into I plus Z into delta I, or in other words delta V is equal to Z into delta I, as V is equal to Z I. So, then therefore, I can write down now of course, here that delta V vector would be is nothing but delta V 1, delta V 2, delta V n transpose. So, then now we can write down this relationship as delta V 1, delta V 2 to delta V n that would be equal to here it is delta I 1, delta I 2 to delta I n. Please again note that all these quantities are complex quantities, and similarly Z 11, Z 12 to Z 1n, Z 21, Z 22 to Z 2n, and so on and so forth, Z n 1, Z n 2 to Z n n. Please note that this element Z 11, Z 12 up to Z n n etcetera, all these are also complex quantities, but just to ease of notation we are not putting any bar of over any of them. Now, suppose that the current injection is changed only at a particular bus k. So, that means now suppose that for delta I j is equal to 0 for all j not equal to k, and j of course, j is equal to 1 to n, and it has got some value at bus k which is equal to delta I k. So, then therefore, in that case what will happen? So, we can write down that delta V 1, delta V 2 to delta V k to delta V n so it would be Z 11, Z 12 to Z 1 n, Z 21 to Z 2 n, Z k 1, Z k 2 to Z k n, n 1, n 2, Z n n, and it would be everywhere it would be 0 0 dot 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 delta I k and 0. So, then from here we can write down that delta V I is equal to Z I k delta I k. It is very straightforward. Delta V I would be Z I k is into delta I k for all I is equal to 1 to n. So, then therefore, delta V k would be Z k k into delta I k. Now, so this is the change in the voltage at bus k due to the change in the injection current at bus k. So, then therefore, if the initial voltage at bus k is V k say 0, then the new voltage is, so then this new voltage would be is equal to V k would be is equal to V k naught plus delta V k, that would be equal to V k naught plus Z k k delta I k. So, now we have got this equation that V k is equal to V k naught plus Z k k delta I k. So, we have got the equation as, so we have got the final equation as V k is equal to V k naught plus Z k k to delta I k. Now, the question is that how do we represent this particular equation as a equivalent circuit. So, now we can represent this particular equation as an equivalent circuit, and this would look like something like this. So, we have got some source, some impedance, then this is bus k, this is bus k, this is the reference, this is the reference, and this is V k, this is V k, this is V k naught, this is Z k k, and the current injected is delta I k, right. So, then therefore, this particular equivalent circuit very easily, very conveniently represent this particular equation. So, V k is equal to this drop Z k k into delta I k plus this drop. So, V k is equal to this drop plus this drop, that is fine. So, then therefore, this is the equivalent circuit of the entire power grid as perceived from bus k and ground. So, we can write down that this is the equivalent circuit. So, this is the equivalent circuit of the power network as seen from bus k and reference. Reference is nothing but ground. So, it is and ground. Now, if I wish to find out that what is the Thevenin equivalent impedance of the entire power grid as observed from bus K and ground. So, then from our very basic understanding of the network theory, we know that whenever we are trying to calculate the Thevenin equivalent impedance, what you have to do, we have to simply short circuit all the voltage sources and simply open circuit all the current sources, and then simply calculate the equivalent impedance as perceived from the given two terminals. Now, in this case there is no open now in this case there is no current source, there is only one voltage source, that is this V K naught. So, then therefore, if we wish to calculate this equivalent Thevenin impedance, so then what you have to do, you have to simply short it. Once you short it, so then therefore, the equivalent impedance between this and this as perceived from bus K would be nothing but Z K K. So, then therefore, we can write down. So, then therefore, Thevenin equivalent impedance as seen from bus K and reference is Z K K. So, this is a very interesting result. So, this is a very interesting concept. Okay. Now, the question is, well, we have found out the Thevenin equivalent impedance of the entire power grid as perceived from bus K and ground, but what about the Thevenin equivalent impedance of the entire network as perceived from between two buses, let us say bus M and bus N. So, let us look at that. So, now we are now trying to find out that what would be the Thevenin equivalent impedance of the power grid as perceived from bus M and bus N. So, towards that goal we assume that now we assume that delta I is equal to 0 for I is equal to 1 to capital N, and I is not equal to M and I is not equal to N. So, then therefore, what we are simply trying to say that only at bus M and bus N there are some perturbation in the injected currents, at all the other buses there is no perturbation of the injected currents. So, then in that case, what we have is, in that case what we have is, we can write down the delta V1, delta V2 up to delta V N, and then Z11, Z12 up to, let us say, Z1N, Z21, Z22, Z2N, this is Zn1, Zn2 up to Zn, and we have 0, 0, something called delta IM, and let us say then delta IN, and then all are 0. So, this is the mth position. So, this is the mth position, and this is the nth position, mth position. So, then from this what we can write down about delta Vm and delta Vn. So, what you can write down about delta Vm and delta Vn? So, you can write down as delta V m is equal to Z m m m m delta I m plus Z m n into delta I n. And similarly, we can write down delta V n is equal to Z n m into delta I m plus Z n n into delta I n. So, these are the perturbations due to the so then these are the perturbations of the voltage due to the perturbation in the injected currents at bus m and n. So, then therefore, we can write down V m final V m is as usual V m 0 plus delta V m. So, then V m 0 is the initial voltage plus Z m m into delta I m plus Z m n into delta I n. Similarly, V n is equal to V n 0, that is initial voltage at bus n, plus delta V n, that would be is equal to V n 0 plus Z n m delta I m plus Z n n delta I n. So, we have got these two equations. Now, we will do some simple algebraic manipulations of these two equations as follows. So, we write that V m is equal to, from here, V m 0 plus Z m m minus Z m n into delta I m. So, what I have done? We have done, I am simply subtracting Z m n into delta I m. Now, because I am subtracting Z m n into delta I m, so then therefore, I must also add it, and if I add it, so then what I will get is, so I get Z m n into delta I m plus delta I n. This is very simple. What I have done? I have simply subtracted Z m n into delta I m and I have added Z m n into delta I m. So, these two cancel out and the original system remains same. Similarly, V n would be is equal to V n naught plus, here what we do is first Z n n minus Z n m into delta I n. So, what I have done? We have simply subtracted Z n m into delta I n. So, then therefore, I have to add this Z n m into delta I n to make this consistent. So, then therefore, if we do that, so we have got Z n m into delta I m plus delta I n. So, this is the equation. So, now we have got these two equations, of course, this equation comes from this. Now, how do we represent these two equations? Can we represent these two equations in an equivalent circuit? So, we would now like to represent these equations in an equivalent circuit. So, when we represent these equations in an equivalent circuit, what we get is, so what we do is, so we say that it is in bus m, this is bus n, so this is bus m, this is bus m, and we have here So, here the voltage is V m, here this voltage is V n, injected current here is delta I m, injected current here is delta I n, and this current goes from here, this current goes from here, they meet together. So, then here this total current is delta I m plus delta I n, and this impedance is Z m n is equal to Z n m. Please note that because Y bus matrix is a symmetric matrix. So, then therefore, the inverse of it. So, that is nothing but the bus impedance matrix will also be a symmetric matrix. So, as a result Z m n would be is equal to Z n m. This would be V m 0, this would be V n 0, this would be Z m m minus Z m n, and this would be Z n n minus Z n m. So, this would be the equivalent circuit. So, from this equivalent circuit what we get, that V m is equal to delta I m into Z m m minus Z m n plus V m naught. So, let us see. So, V m is equal to V m naught plus delta m into Z m m minus Z m n plus Z m n into delta m plus delta I n, and V n is equal to V n naught plus Z n m delta m plus delta n plus this. So, then this circuit faithfully represents these two equations. So, then this is nothing but, so this is nothing but the equivalent as perceived from bus m and n. So, this is the equivalent circuit as perceived from bus m and n. Now, from here I can find out practically everything. Now, if I want to find out the equivalent impedance as perceived from bus m to ground, so what I get? So, first thing we have to, what we have to do, we have to make these two sources short circuited. So, once we do this short circuit, and then if I wish to find out that what is the equivalent Thevenin impedance as perceived from bus m and ground. So, then what it would be? This would be Z m m minus Z m n plus Z m n. So, this and this cancels out. So, Z m m remains. So, then therefore, from this the equivalent Thevenin impedance between bus m and n, bus m and ground would be equal to Z m m, which we have already seen. Similarly, as observed from bus n to ground, we can find out that the Thevenin equivalent impedance would be Z n n minus Z n m plus Z n m. So, then this particular Z n m cancels out, and so then therefore, the Thevenin equivalent impedance as perceived from bus n and ground would be equal to Z n n, which is absolutely correct as we have already observed. Now, what would be the Thevenin equivalent impedance as perceived from bus m to n? So, then for that what we have to do? We have to simply make our journey from bus m, and then we have to simply finish our journey at bus n, and then we have to simply add, and then we have to simply see that what are the impedances we get. So, then when we start our journey at bus m and then finish our journey at bus n, we find that this impedance and this impedance are in series. So, then therefore, the Thevenin equivalent impedance as perceived from, so Thevenin equivalent impedance as seen between bus M and N is, this is denoted as Z Thevenin M N, and that is given by Z M M minus Z M N plus Z N N minus Z N M. So, then therefore, as Z M N is equal to Z N M, so then therefore, Z Thevenin between bus M and N is given by Z M M plus Z N N minus 2 Z M N. So, this is a very powerful and interesting result. So, then therefore, you can find out that once we know the bus admittance matrix of a system, then we will simply take the inverse, we will find out the bus impedance matrix, and once we find out the bus impedance matrix, from that bus impedance matrix elements we can readily calculate the Thevenin equivalent impedance of the entire power grid as perceived from bus M and N. Of course, here we have actually written down this particular expression due to this fact that Z M N is equal to Z N M, right, and this is due to this fact that my bus impedance matrix is basically a symmetric matrix. So, in this lecture we have looked into the Thevenin equivalent impedance of the entire power network. First, we have looked into the Thevenin equivalent impedance as perceived from any particular bus to ground, and then we have looked into the Thevenin equivalent impedance as perceived between any two given buses. So, in the next lecture we would be continuing this particular discussion. Thank you.